Hello. In this video, we are going to look at solving homogeneous linear systems of differential equations with constant coefficients that have repeated eigenvalues. Let's just jump in with an example and see if we can figure it out from there. All right, so let's suppose we have x prime equals 1, -1, 1, 3 times x. So there's our system of differential equations that's homogeneous with constant coefficients. So what we do is we start off, just like in the last two videos, we start off by just picking for x. We have chi e to the RT, and then x prime equals chi r e to the RT. I think it's xi, not chi. And anyway, whatever. Anyway, take these, plug them in. We get to here. You can go ahead and cancel the e to the RTs, and then what's left? This is the eigenvalue eigenvector problem. We have a times a vector x equals lambda times x. And so we can go through and solve this by using the eigenvalue eigenvector problem steps. And so if you haven't seen that before, if you're a little bit lost, you want to go back and watch the previous videos where we go through in a little bit more depth how to solve, how to get to this point, like from here to here. All right, so we can get to here, and then what we want to do is take the determinant of our 2x2 matrix. And we want to set it equal to 0. So if we do that, we get 1 minus r times 3 minus r plus 1 equal to 0. We get r squared minus 3r minus r, that's going to be minus 4r. We have plus 3 plus 1, that's plus 4 equals 0. And we get r minus 2 squared equals 0. That gives us r equals 2. All right, so this is an eigenvalue that has, that's a repeated eigenvalue. It's repeated twice. That's what the square here represents. Okay, so let's just ignore that for the moment, however, and let's go through and pretend, okay, we'll have a problem when we go to the point where we need a second solution, but let's go ahead and find the solution by just using the one eigenvalue that we've got. So we go ahead and take that eigenvalue, r equals 2. We plug it in to this system right here. We're going to plug that in, and then we're going to go through and find the xi vector, and that will be our eigenvector. So when we plug in 2, we're going to get 1 minus 2. That'll be -1. And then we've got -1 again. And then we've got 1 and 1. Times xi equals 0. And then to solve this, figure out what xi's work in that, we're going to go through and we're going to change over to an augmented matrix. So we'll have -1, -1, 0, 1, 1, 0. Row reduced to reduced row echelon form. We get 1, 1, 0, 0, 0, 0. Then we can translate back to a system equation system format. So we're going to get, this is our coefficient. So 1 xi1 plus 1 xi2 equals 0. And then our free variable will have xi2 equals xi2. And then this we can rewrite as xi1 equals negative xi2 and xi2 equals xi2. And finally, we get xi equals -1, 1 times xi2. And then that can serve as our first solution. Okay, that gives us our eigenvector. When we combine it with our eigenvalue, we can put them together and get our first solution. So we're going to get x1 equals -1, 1 times e to the 2t. And where did that come from? That came from just taking this format here that we said let x equal this. We found out what xi was, and we found out what r was, and we just took them and plugged them in. And that gets us our first solution. All right, now we need a second solution. And the problem is that we do not have a second eigenvalue. All right, so plugging in 2 again is not going to do anything for us. It's just going to get you the same information. We need another eigenvector. We need something different than this. We can't just have this solution multiple times. The Wronskian will be 0. It won't work. All right, so what can we do? We can go through and we can think back to when we were working with second order equations, and we were we were trying to go through and figure out what to do when we had repeated roots to the characteristic equation with those second order equations. And what we did is we went through and we tried something like, we tried adding a t, right? So we tried something like this. Okay, so what we're gonna do is we can let x equal this and then see if it gets us. So this is not the same xi as previously. This is a new xi. And we can go through and see if we can find a xi that works for this. And if so, then this would give us a second solution. We could just pop that in. We've already got the r. We would be good to go. All right, so what happens if we go through and do x prime? Then we're going to get, got to do the product rule here. So we got t times 2e to the 2t plus e to the 2t times 1. So we're going to get xi 2 xi e to the 2t plus xi e to the 2t. Okay, and so that was all. So what we're doing here is we're basically repeating the stuff that we did at the beginning, just with a different guess, a different let. Okay, and so just as a shortcut, rather than to kind of jump back and forth here, I'm going to go through and replace this with a, because what we're going to find that we're going to have a problem. All right, so let's say that we had x prime equals ax. Okay, so we're just not going to put the a in because it's just to save space. If we did that, x prime is going to be, we're going to have 2 xi t e to the 2t plus xi e to the 2t, and then we would have a times x, which is xi t e to the 2t. Okay, and then if we went through and rewrote this, we would have xi e to the 2t equals a xi t e to the 2t minus 2 xi t e to the 2t. Oh, by the way, we can cancel all these e to the 2t's. Cancel all those. And then this we could rewrite. This is xi. And then we would have, we could go through and we could take the at here at minus 2t. We could pull that out, make that into a. Actually, we're just going to take the a minus 2. We can take a minus 2i, pull that out, and then we would have t left. So we're just basically factoring out the t here. Oh, and the xi, sorry. We're factoring out the t and the xi. All right, so if we went through and did that, so what would happen here? So here's the issue, this a minus 2i. The question is, what is that? Well, if you go back, all right, this thing here, this was a minus 2i. Okay. Or sorry, yeah, this was a minus ri. And then this was a minus 2i. So what do we know about a minus 2i times xi? That equals 0. Yeah, so this is a little bit unclear. This is a minus 2i right here. How did I get that? So just recall this right here. This was a minus ri. That's part of the eigenvalue eigenvector problem. And then what we did is we found out that r was 2. That's right there. We plug that in. And when we plug that in, if you plug in r equals 2 into this, that gets you a minus 2i. And then this matrix becomes this thing here. And we know that this times xi equals 0. All right, and so what all that means is it means that this is 0. And if this is 0, then it forces xi to equal 0, right? And we did not end up getting another solution. So basically we failed in our steps here to go through and get another xi. Okay, so this didn't work. By going through and letting x equal xi t e to the 2t, by just adding a t, it didn't work. It was not sufficient. All right, so it did not get us a second solution. However, what you can do from that is, instead of just giving up on the idea, what we can do is we can just make this a little bit more complicated. Effectively, what we're going to do is we're going to go through and try again. And what we can do is we can let x equal xi t plus eta times e to the 2t. So what we're doing is, instead of doing just a t multiple of xi e to the 2t, we're doing xi t, but it's a t plus another constant. Okay, so this essentially, this is like the equivalent earlier. You know, we went through and we were solving a differential equation, and we were solving, you know, e to the rt was our guess, and then we went through and tried t e to the rt, and then the idea is that when we tried this, it didn't work, and so what we did is we're trying, you know, t plus, you know, c e to the rt. We're basically adding another constant in there to see if that constant helps. So we're still having our t multiple, that's right here, but we're adding this extra term eta to represent, you know, constant multiple, and see if that solves the problem. And it turns out that it will. All right, so that's the key here, is that it was not sufficient to go through and just use a t multiple of our solution, right? So we went through and started off with this, but just adding a t was not enough. We needed to add t plus essentially another vector. All right, and so if you do that, so this is, if you write it out, you get xi t e to the 2t plus eta e to the 2t. Then if you do that, so x prime is going to equal xi t 2 e to the 2t plus e to the 2t plus 2 eta e to the 2t. We can clean this up. This is 2 eta t e to the 2t plus xi e to the 2t plus 2 eta e to the 2t. All right, and that gives us our derivative. And now if we go through and take all that and plug that into our x prime equals ax, let's see what happens. Okay, so we're going to get all of this on the left-hand side. So we're going to get 2 xi t e to the 2t plus xi e to the 2t plus 2 eta e to the 2t equals a times, and then this will have xi t e to the 2t plus eta e to the 2t. All right, and then we can go through and we can do some simplification here. T e to the 2t, e to the 2t, and so on. And now we're going to multiply through by a. So we're going to get a xi t e to the 2t plus eta plus a eta e to the 2t. So one of the things we can do is we can go through and we can cancel all the e to the 2t's. Okay, and then next what we're going to do is we're going to group things. So things that have t in them, we're going to group. So we'll have 2 xi t equals a xi t. And then, so that's this and this. So those have to be equal. So the things that have t have to be equal. When we go through and you have an equation like this, if you've got variable, you know, if you've got t terms, then the coefficients of the t terms have to be equal. So that's kind of what we've done here. And then you're going to have xi plus 2 eta equals A eta. Okay, so this is non-T stuff, T stuff. All right, and then now here you can cancel the T's. And then if you rewrite this, we can move the 2 over, and you're going to get, this is going to turn into A minus 2I times xi equals 0. Okay. And then here, if you go through and move this over, and I'm just going to swing this around, you're going to get A minus 2I times eta equals xi. So you get these two equations. Now, if you note this first equation, that's the problem that we've already solved. Okay, so that was this A minus 2I times xi. You know, that was this, all this stuff that we went through and did, that was solving that first problem. So we know what xi is. We know what the solution to that is. It's going to be -1, 1. So we can go through and basically just by looking at this can tell us we can inherit, and we can just, you know, grab the xi from earlier, and that's going to be the solution to this piece here. And then once we have that xi, we can then take it and plug it in over into our second equation, and then we'll only have one unknown eta, and then we can go through and solve for eta. Okay, so we can go through and solve it. So basically we have like a system of equations here. So there's one equation, here's a second equation, and you just go through and solve them one at a time. You first solve this one to get eta, to get xi, which we already did earlier. We can just inherit that. You don't need to do it again. And then you can just take that, plug it into the other equation, and then we can use that as a solution to go through and solve the other equation. And in so doing, we can get the xi and the eta that we could plug into this, our guess, and then we'll have our second solution. Okay, so it's a little bit convoluted there, but that's the method, right? So if you have this as your guess, then the consequence is you get two equations, one of which we've already solved, and we can just grab the solution to that. And so there's really only one new thing to do. Okay, so that's kind of cool. So we can just really just jump right to that. Okay, so that's what I'm going to do. I'm going to try to make this as unconfusing as possible, right? So this A minus 2I, what is A minus 2I? That was the matrix here that was next to xi that we set equal to 0. So we've already done that. What was that? Let's just take another look. It was this guy right here was A minus 2I. So we just want to inherit that, grab that again, because it's going to be the same thing. All right, so we're going to get -1, -1, 1, 1 times eta. And then on the other side of my equation here, I'm going to put xi. So what was the xi that we got earlier? We can look back at it. It was -1, 1. So we can just grab that and put it over here, -1, 1. Okay, now that once we've done that, we can go through, we can turn this into an augmented matrix. So we get -1, -1, -1, and then 1, 1, 1. Okay, and then we can go through and do our row reduction. So we get 1, 1, 1, 0, 0, 0. And then from that, we can now translate this back to our system format. So we've got, this is the coefficient, 1 eta 1 plus 1 eta 2 equals 1. And then eta 2 equals eta 2. That's our free variable. And so then we can go through, this is eta 1 equals negative eta 2 plus 1. Eta 2 equals eta 2. Combine those, we get eta equals -1, 1 times eta 2 plus 1, 0. Let me just check one thing here real quick. Okay, looks good. All right, and so this gets us eta, and now we can go through and take that solution, take our previous solution for xi, which we kind of inherited, grabbed from earlier, and then we're going to take them and plug them into this to get a second solution. and some nice things happen. So this is going to be x2. Here's our second solution, and we're going to do -1, 1 times t e to the 2t, right? It's I, we just found it, or we grabbed it from earlier because this is the same problem we solved earlier. T e to the 2t, so that part is right there. And then plus, and now I'm going to substitute in what I found for eta, which is this. So we're going to have -1, 1 times eta 2 plus 1, 0 times, so eta, just pop that in there. That's what we just found, times e to the 2t. Okay, and so we're not done yet. This is -1, 1 t e to the 2t plus -1, 1 times xi2 e to the 2t plus 1, 0 e to the 2t. Okay, and so now I intentionally multiply that out so that you can go through and take a look at this. All right, so take a look at our solution here. We have this part, this part, this part. So we got this, still have this xi2 in here. Okay, and so we want to do something with that, get rid of that some way. And now what we're going to do here is we're going to note, look at our first solution. Our first solution was -1, 1 times e to the 2t. And we know at some point we're going to go through and take linear combinations of these two solutions. And so we're going to end up taking multiples of this solution eventually. So we're going to eventually have a C1 that we're going to put in front of this to just say all multiples of this is a solution. Now take a look at this. It's the exact same thing, right? It's got the we've got -1, 1 e to the 2t, and then we said we're going to put a C1 in front to represent all multiples of that. -1, 1 e to the 2t, and we've got eta 2 instead of C1, but they amount to the same thing. It's the same idea that you're just going to take multiples of them. All right, so what we have is we have the first solution is embedded within our second solution when we write it like this. And so what we can do is we can just go through and say, you know what, this is the first solution. We've already got we don't need the first solution. We've already got that. And so we can go through and simplify the second solution into -1, 1 t e to the 2t plus 1, 0 e to the 2t. Okay, and so this is our second solution. We've already got our first solution earlier. And so what we can do is we can just take the linear combination of the two, and that will be our final solution here. So we're going to have C1 times our first solution, which is -1, 1 e to the 2t plus C2 times our second solution, which is -1, 1 t e to the 2t plus 1, 0 e to the 2t. Okay, we can go through and we can calculate the Wronskian to make sure that those two solutions are different enough. If you do that, we're going to have the determinant of the 2x2 matrix. So you want to use this as your first column. And so you need to multiply the e to the 2t in there. So we're going to have negative e to the 2t, positive e to the 2t. And then for the second, we're going to have negative t e to the 2t. That's the top here, plus e to the 2t. And then for the bottom, we're going to have just t e to the 2t. And so if you multiply this out, we're going to have this times this. So we're going to have negative t e to the 4t. And then we're going to have minus this times this. So we're going to have a minus times a minus. That's going to be plus t e to the 4t. And then then this times this with a minus is going to be minus e to the 4t. All right, and then if you simplify this, these cancel, and we get negative e to the 4t, which we know is not equal to 0. So these two solutions are sufficiently different that it gets us all of the solutions. We can go through and graph / sketch this, create this the phase portrait. The phase portrait is on an x2, x1 axis. All right, so to do that, we want to go back and set C2 equal to 0. If you do that, you're going to get x equals C1 times 1 negative 1 times e to the 2t. This gets us x equals x1, x2, which equals C1 e to the 2t, negative C1 e to the 2t. And so we get x1 equals C1 e to the 2t, x2 equals negative C1 e to the 2t. And if you put these together, that tells us that x2 equals negative x1. Okay, so let's go ahead and draw a coordinate axis. This is an x2, x1 plane, and we've got x2 equals negative x1. That would be our line with a negative 1 slope that goes to the origin. And so we've got a positive exponent here. And so what does that tell us? Is that it tells us as t increases, we move away from the origin. Okay, so so far so good. Then we need to go through and find the second piece, right? So this is x1. So we need x2. We need to put x2 on here. All right, so to do that, we're going to go through off to the second page. We're going to say, all right, let's set C1 equals 0. If we do C1 equals 0, we're going to get x equals C2 times negative 1, 1, t e to the 2t, and then another C2. So I'm distributing the C2 here just to kind of speed things up. 1, 0, e to the 2t. And so this is going to give us x1, x2 equals negative C2 t e to the 2t plus C2 e to the 2t over C2 t e to the 2t. And so we're going to get x1 equals negative C2 t e to the 2t plus C2 e to the 2t, and x2 equals C2 t e to the 2t. Okay, so the problem that we run into here, so if you look back on the previous example, we had, notice how the right-hand side are really similar. You can go through and make a very minor change to make the right-hand sides the same. So basically you multiply the top one by a negative, and that turns you have negative C1 e to the 2t, and you'll have negative C1 e to the 2t. So we can't do that here. So this is too complicated for that. These two things are the same, but this one isn't, right? And so the easiest way to go through and figure out what this looks like is, like in the last section, is to go through and depend upon a parametric equation grapher. So the C2 in this case just acts as a multiple, and so you can just drop off the C2. It will basically, the C2 just enables us to go through and just stretch both the x1 and the x2 coordinate by an equal amount. All right, and so we can just go through and ignore it or treat it as C2 equals 1. So you can go through and treat it as C2 equals 1, and we can get some idea of what the problem is going to look like. All right, so I've already gone through and done that. And so this is what we get. All right, so I've gone through and I've plugged in our equation, except missing the C2, and this is what it ended up looking like. It looked like this thing that starts off at the origin and it curves away, and then ends up, if you zoom out a little bit, you can see what happens. A little more. All right, so it eventually kind of tails off and it just, moves in this kind of this direction. Actually, if you go through and take the limit as this goes to infinity, what you're going to get is you're going to get -1, right? That is approaching a slope of -1 as you if you take the ratio between these, you're going to end up getting a slope of -1. Okay, so that tells us part of what the object looks like. All right, hold on. If I can get it to stop. Never mind. People making people sick. Yeah, I'm doing one notch on my mouse and it's like going way in and way out. So that's what it looks like. If we go to back to our whiteboard here, we can go ahead and put that in. So what did that look like? It looked something like this. Okay. All right. And the question is, well, this had kind of two pieces. Does this have two pieces? The answer to that is yes. If you go through and instead of having C2, instead of replacing C2s with positive ones, if you go through and replace C2 with negative ones, you'll be able to figure out, what's another option for what this looks like. And to do that, you can go in your plotter here and replace that with a positive and replace this with a negative and replace this with a negative. And you can see we get the reflection, okay? And the same thing happens if you zoom out. It ends up eventually approaching -1 in there as well. Okay, so it kind of curls around before it ends up going over into, quadrant 4, moving off in the, slope of -1 direction there. Okay, and so we can take that and add that to our picture as well. And that gives us x2. Right, and then just like the first section that we went through and covered here, once you've got x1 and 2, we just want to take linear combinations. And the way that's going to work is you're going to basically just kind of try and move toward whichever one of x1 or x2 you're closer to, because that one's going to be stronger. And in effect, it's going to end up looking kind of like this. You're going to have like something like this. You'll have something, kind of like this. If you have a curve here, it's going to look like that. And then the same thing over here, we'll have between these, between them, and same thing here. And that's what we end up getting for our phase portrait. Okay. And that's the finished problem. All right. So with these, you want to go through and find the solution and then sketch the phase portrait. Let's go through and try a second example, just so you have two of the problems to look at. And then this one, we'll go through and we'll do it without, basically as minimal as possible, without going through and jumping through all the explanation like from the last one. So if we have -3, 5/2, -5/2, +2 times x, we go ahead and we said let x equal xi e to the RT. We get x prime equal xi r e to the RT. Take these, plug them in. You get xi r e to the RT equals -3, 5/2, -5/2, 2 times xi e to the RT. E to the RT's cancel. This is the eigenvalue eigenvector problem. Move things around, you get -3 minus r, 5/2, -5/2, 2 times xi equals 0. we want to go through and, oops, forgot my minus r here. We need to go through and calculate the determinant when the determinant is 0. So we have the determinant of -3 minus r, 5/2, -5/2, 2 minus r. That's going to equal -3 minus r, 2 minus r, plus 25/4. That equals r squared. We have a -2r and a +3r. So we're going to end up with plus r. And then we're going to have -6 plus 25/4. All right, so -6 plus 25/4 is going to be plus 1/4. Then we can set this equal to 0. And this is r plus 1/2 squared equals 0. We get r equals -1/2. So again, only one eigenvalue that is repeated. Take that one eigenvalue, plug it in. So when you do, we should get -5/2, -5/2, 5/2, 5/2 times xi equals 0. Now let's just check that. -3 plus 1/2, that's going to be -5/2, and then 2 plus 1/2, that's going to be +5/2. Oop, hold on. I got reversed. Good thing I checked, right? Okay. And then from there, we can go through and form an augmented matrix. We're going to get -5/2, 5/2, augmented with 0, -5/2, 5/2, augmented with 0. This gives us, if we row reduce this, this is 1, -1, 0, 0, 0, 0. Translate back. This is the coefficient of xi1. Coefficient of xi2 equals 0. Xi2 equals xi2. Xi1 equals xi2. Xi2 equals xi2. Xi equals 1, 1, xi2. All right, and then we can then take, this came from r equals -1/2. Right, yep. And then we can take those and get our first solution. X1 equals 1, 1 e to the -1/2 t. All right, now to go through and find our second solution, what we're going to do is we're going to skip some steps that we did in the last problem. Okay, so let's just take a look. I said I wouldn't do a lot of explaining, but I'll do a little bit because otherwise it's going to come out of nowhere. Right, so we just went through and solved this. We just went through and found what xi is. So the next thing we want to do is we want to do a minus 2i. That's the same matrix we just created to solve for what xi was. We want to take that, multiply it by eta, and set it equal to the xi that we just found. Okay, so for the second solution, we're going to go through and we're going to let x equal xi t e to the -1/2 t plus eta e to the -1/2 t. And then the consequence of that is we're going to get this guy right here. This is a minus -1/2 I. So we're going to take that, and instead of multiplying it by xi, we're going to multiply it by eta. We're going to have -5/2, 5/2, -5/2, 5/2 times eta equals xi, which is 1, 1. All right, so one more time, I'll show you where that came from. So that is when you go through and you let let x equal xi t e to the 2t plus eta e to the 2t. The consequences, you get these two equations. This one we've already solved. We want to take the xi that we got from that one and just pop it over on the right-hand side of this second equation where we have the same matrix that we used in the last one times eta equal that xi. And that's what I just did. All right. The same matrix that I used to find xi right there, copied exactly over, times eta equal to the xi that we just got, which is right there. Okay. And so from there, you want to go through, form the augmented matrix, negative 5/2, 5/2, 1, negative 5/2, 5/2, 1. You want to row reduce this. All right, so what are we going to get here? So we're going to multiply through by, this is actually a little bit more complicated because we got to make sure we get the right answer over here for this. So we're going to multiply by negative 2/5. That will get us a 1 here. Negative 2/5, that's going to get us a negative 1 there. And then we're going to have negative 2/5 times 1. So we'll have a negative 2/5 there. So we're going to have 1, negative 1, negative 2/5. And then all zeros. Because the rows are the same. So you can take this one, multiply by negative 1, add it to this one, and wipe it out. Okay. And then once you've done that, now you can go through and translate this back to a system. We've got eta 1 minus eta 2 equals negative 2/5. And we're going to have eta 2 equals eta 2. And then from that, we can go through and say eta 1 equals eta 2 minus 2/5. Eta 2 equals eta 2. And then finally, we get eta equals 1, 1 times eta 2 plus negative 2/5, 0. Okay. And so now that we've done that, we can go through. So all this came out of letting x equal this. So we've got the xi. That's the same xi from earlier. That's the 1, 1. You can just pop that in. We can just inherit that. Okay. And then the eta, we just went through and found that. But recall in the last time we did this, what ended up happening? What ended up happening? The term that had the eta 2, that ended up canceling out. And so the only thing that we ended up caring about was this piece of the eta. All right, this guy right here. All right, so what we can do is we can go through and just grab that to get to our second solution. Okay, so what we care about is we care about this. And so by taking that and combining it with our xi from earlier, we can get the second solution. So x2 is going to equal our xi, which is, what was it again? It was 1, 1. So we're going to get 1, 1 t e to the negative 1/2 t. And then plus this thing, right? This guy, this is the one that ends up canceling from earlier. And so we want this guy. So that's going to be negative 2/5, 0 times e to the negative 1/2 t. Okay, and so that's the kind of the speedy way to go through and get the two solutions. All right, so we can just kind of recap. All right, so we start off, here's our equation. We go through let x equal xi e to the rt. That enables us to go through and find an eigenvalue. We've only got one. With that eigenvalue, we find the eigenvector that goes along with it. And then what we do once we've got that eigenvalue and eigenvector is we go through and we let x equal this. And then we're just inheriting all the consequences of this from the first problem we did, which is we take the matrix that we used earlier right there, multiply it by eta and set it equal to the eigenvector you got, 1, 1, the xi vector, and then go through and solve that. Once we do that, you're going to get something that looks like this. This term ends up canceling away because that's the multiple of the first solution. So we only care about this part here. Take this, put it in place of the xi here, put it in place of the eta here, pop in the xi from our first equation, and we've got our second solution. Okay, and so x is going to equal c1 times 1 e to the negative 1/2 t. That's our first solution, plus c2 times 1 t e to the negative 1/2 t plus negative 2/5 0 e to the negative 1/2 t. Okay, I think that's about as fast as you can go through and solve these. That's about as minimal steps as you can do. All right, so that's our solution. And then the last thing we can do is we can go through and graph/sketch this. Yes, the phase portrait. And so we do C2 equals 0. That gets us x equals x1, x2, which equals C1, 1 e to the negative 1/2 t. So that's going to equal C1 e to the negative 1/2 t, C1 e to the negative 1/2 t. And we've got x1. These are the same, right? So we're going to have x2 equals x1. Okay. And then for our second solution, we can do C1 equals 0. We're going to have x equals x1, x2 equals C2, 1 t e to the negative 1/2 t plus C2. Actually, enough from there. Let's drop down below. Plus C2, negative 2/5 0. Right, that's what we got, right? Yep, negative 2/5 0 e to the negative 1/2 t. And if you multiply all that out, we're going to get x1 equals C2 t e to the negative 1/2 t minus 2/5. Sorry, forgot the C2 there. C2 2/5 e to the negative 1/2 t. And x2 is going to equal C2 t e to the negative 1/2 t. And that's it. We got the 0 here. That kills it. Okay, so let's go ahead and try to do our face portrait. We have x2 equals x1. That's going to be the line that goes to the origin that has positive 1 slope. We have negative exponents, right? Negative exponents. That means we have the solutions go toward the origin. Okay, and then for the second solution, we're going to go ahead and take our parametric equation here, and we're going to pop it into a parametric plotter. And I've already set that up. It looks like this. Okay, so we've got t e to the negative 1/2 t minus 2/5 e to the negative 1/2 t, and then t e to the negative 1/2 t. So it kind of starts off going this way and then curls around. And so we can go ahead and put that on our picture. So it starts off and going kind of along the curve here and then curls around. Oops. More than I intended there. Okay, and we still have a negative exponent here, so it's still going toward the origin. Just does this curl action. And then you can go through and negate the parametric equation. And if you do, then you're going to get the reflection of this. So it's going to look something like, and again, same thing. This is going in to the origin. And then from there, you can go through and just kind of combine. So these are the two solutions. This is x1. This is x2. You just kind of go through and combine them. So these two, combine them, you get this. And the reason we're combining them is because we're trying to graph all the linear combinations. So the idea is we're taking, points that are, out here, and we're just taking, averaging these two things, and whichever one's closest is going to have the larger effect. So if you started off here, you'd go something like this. If you started off here, you'd go something like that. And then between the two, you can kind of just go through and average them. And same thing over here. And that's what our phase portrait looks like. And that's the way that you can go through and generate it. Okay, so you can use this guy, which is pretty easy, and to figure out. And then for the second one, the one that's harder, you can break out the parametric equation grapher. Okay, so that's how you go through and do it. I think that's about as fast as you can go. So there's your solution, and then you can come up with the phase portrait. Okay, so that is how to go through and solve linear systems of differential equations that are homogeneous, that have constant coefficients, and that have repeated eigenvalues. Thank you for watching, and I'll see you next time.